This week we're going to do more number theory. Last semester we literally did 1 week of number theory and then 10 weeks of geometry after that. But that's basically because there's so much geometry, like there's so much knowledge you have to cover in geometry, and not as much for number theory, to the extent that it will actually help you for the Mathcounts competition. So that's why we're doing it again. We're going to focus more on new content this time. So more number theory, let's go. Topics, I'm going to first go over like your general number theory tips. Whenever you see a number theory problem, what are your first steps? What is your first reaction? What should you do first? And then I'm going to do some extra divisibility rules, some extra ones that I did not cover last time. We're going to do some review problems, and then we're going to do arithmetic and basis and digits. Okay, so we're going to do a little bit of review problems just to get you back on track with how divisibility and mods work. Okay, so here are some general tips. Hello, everyone. Okay, so here are some general tips on what you should do when you see when a number theory problem. You should first write down trials to find patterns. So the key about many number theory problems is it's just patterns, right? Remainders are patterns, right? If you have something mod 7, the remainders go 0, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6. It goes in a pattern. And as you'll see later for digits, finding patterns is a key part of your how to solve the problem. Okay, so a lot of number theory is based on patterns, and you're going to deal with really big numbers in number theory a lot, and writing down trials to find patterns allows you to basically rationalize and reason what the value should be for whatever and solve a problem you're solving. Yeah, and then that leads me to the second point, which is somehow make the numbers smaller. You're going to deal with really big numbers here, and basically you're going to have to reason out, oh, what property of this really large number to have to find is similar to a smaller number, and is that smaller number easier to find? Okay, and then there's this really tricky one, which is see if there's a way to use sequences in series. Number theory is very, very closely related to sequences in series. So find a way to, like, if you're really stuck, look for ways to put in a sequence or series, solve for a series, for example, because those are basically patterns as well, right? So number theory has a lot of patterns, sequences and series also a lot of patterns. So naturally they would go together. And the final one is basically a given that you have to do every time before you do any math competition. You have to do this before every math competition, which is basically you memorize the prime factorization of the year you're taking the test in. So this year is 2021. That is 43 times 47, which is very fascinating, right? All right, so in a lot of problems, in a lot of math competitions, you're gonna have to use the prime factorization of the year you're in. This number is probably gonna pop out sometime in the competition. So it's always best to memorize the prime factorization, because if you wanted to prime factorize 2021, it's really hard, right? If you see it's 43 times 47, it's not an easy prime factorization to do. Okay, so memorize that. And in the future, always memorize the prime factorization of the year, right? Next year, you would have to memorize the prime factorization of 2022, 2023, all the way until you stop doing math competitions, okay? That's a given for any competition. So now we got some extra divisibility rules. Here are these two. We have the divisibility rule for a times b. If we have a number that's a times b, we can factor it out to a times b. And a and b are relatively prime. This is critical. Then the divisibility by that number, a times b, is the same thing as satisfying the rules for a and b separately. Okay, I didn't explicitly say this last time, but this is basically the idea. And what relatively prime means is no common factors other than 1. Okay, for example, 8 and 6, they are not relatively prime because they have 2 as a common factor. So basically the GCF of A and B is 1, literally, okay? So 3 and 5 work, okay? So basically, this is why the rule for 6 works. If you remember, the rule for 6 was 6 means it satisfies 2 and 3 separately, right? And 2 and 3 are equal to 6, and 2 and 3 are relatively prime, which is why that works for 6, okay? And then we have another one, 2 to the nth power for some integer n. The last n digits are divisible by 2 to the n. So as an example, for 2 to the 1, the last 1 digit divides by 2, right? That makes sense, right? If the last digit of a number is divisible by 2, the whole number is divisible by 2. That basically means it's even, right? If we have 2 squared, that means the last 2 digits divisible by 2. This is by 4, right? 2 squared. And that's the rule for 4, right? So basically, this is the pattern for any power of 2, the rule for any power of 2. Any questions here? Cool. Now we're going to do some review problems. Got these 2 really interesting problems here. And as a hint, use mods. Okay, use modular arithmetic. I'll give you, these are pretty meaty problems, so I'll give you guys 6 minutes. You can private chat me your answer when you get it, and I'll tell you if you're right or not. Okay. So I'm going to go over these now. First one, this number 9999995 is divisible by 15. So what's the rule for 15? We don't have a rule for 15, but if you notice, 15 is 3 times 5, which means if it satisfies the rules for 3 and 5 individually, the whole number is divisible by 15. Well, obviously, it's divisible by 5. The last digit is a 5, so we can literally get rid of this 5. We just need to prove it's divisible by 3. There are 47 nines in front of the 5, and then a mystery digit in front of the 9s. What are the possible values for the mystery digit? So what's the rule for divisibility by 3? We add all the digits, and if that number is divisible by 3, or in other words, if that number is 0 mod 3, that number is 0 mod 3, and the whole number is divisible by 3. So if we add all the digits, it should be 0 mod 3. So let's say the first digit is x. We got x, and then we add 47 nines here. And then we add a 5. This must be 0 mod 3. We got to solve for x here. Notice how 9 is 0 mod 3. So if 9 is 0 mod 3, we can replace 9 with 0. And that term literally goes away, because 0 times anything is 0. Now all I have is x plus 5 is 0 mod 3. So now we can literally just test values here. 1 works. 1 plus 5 is 6. 4, 7. And that's it. Okay, 1, 4, and 7. And these are the 3 possible values for the mystery digit. Okay, x plus 5 equals 0 mod 3. Now the next one, we got a ton of 8s divisible by 45. 45 is 9 times 5. So note that we have to do this because if we do something like 15 times 3, that doesn't work. Because 15 and 3 are not relatively prime. So we have to do it so that it's 9 times 5. Obviously, it already satisfies the rule for 5. We just need to prove it's a multiple of 9. So the rule for 9 is we add all the digits, that's 0 mod 9. Let's add all the digits then. We got a mystery digit, x, and we add 71 eighths. That's 78. 71 times 8 plus 5. Has to be 0 mod 9, okay? 71 times 8, that's a really complicated one. We can't really turn that into 0 mod 9, because 8 is not 0 mod 9. So what I actually would do, you could do this right now. You could evaluate 71 times 8 and add 5 to it. No problem. But if I turn 8 to negative 1 mod 9, we got a lot simpler, right? Instead, I'm just minusing 71 here then. Negative 71. If I do that, then it's x plus 60 minus 66. Right? And what is negative 66 mod 9? Well, negative 72 is 0. So if we add 6 to it, we get to negative 66, which means that negative 66 must be 6 mod 9. So this is 6 mod 9. We add 6 then. So how many digits is x plus 6 equal to 0 mod 9? We got 3. 3 plus 6 is 9. What about 18? X plus 6 is 18, 12. Well, 12 can't be a digit. So that means 3 is the only value. And that's the answer. Okay? So you could evaluate 71 times 8. That would work for sure. But you could make a mistake along the way, which would make your answer go wrong. Okay? So a really good trick is to write negative mods. If that makes things easier, write negative mods. Skip this one. I'll put that in the homework. It's very similar. Now we got these really nice mod problems. 3 of them. 3 parts. I'll give you 5 minutes. All right, go over these now. So you have this really big number. What is that number mod 3? You could use an arithmetic series and add all those together and divide by 3, but that would take a while, right? So we don't really want to do that. Let's actually just look at the numbers, because we can simplify them a lot by just using our mod rules, right? We can turn all of these into just the remainder. That's 5, 6. Always write a bit more. And then we have all the way to 1,000. 999 plus 1,000. What's this mod 3? Well, we can take all the multiples of 3 out, right? Because those are just 3 mod 3, which is 0 mod 3. 1 plus 2. We can't really change those, right? 5 and 4 can turn into 1 and 2. We take the remainders. 7 and 8, those can turn into 1 and 2 as well, because 7 is 1 mod 3. 8 is 2 mod 3. Now you can see we have a lot of groups of 1 plus 2. 1 plus 2 is 3. And 3 is 0 mod 3, so those go away. All groups of 1 plus 2 will go away. So basically we have nothing. We literally have nothing, right? It's all 0 all the way up until 999, because that's the multiple of 3 we have here. But then we add 1,000 more. And 1,000 is 1 mod 3, so the answer is 1 mod 3, because everything else before that was 0 mod 3. Good? Okay. The next one, you can do the same approach again. That would work. It would work. But there's just a sneakier way to do it. You apply the arithmetic series now. So we do that. We take the average of the first and last terms and multiply them by the number of terms. We find what this is mod 4. Well, if you look here, 1,000 is 0 mod 4. The whole thing goes to 0, so this is 0. All right. So by applying the arithmetic series, we know that this is automatically 0. We can do the same exact thing for mod 5. 1,000 is 0 mod 5. The whole thing disappears, so it's 0. Okay. So you could have done it the way we did for mod 3, but there's a lot easier to do, a lot easier way to do it. But for mod 3, the reason why we couldn't do this is because 1,000 is not 0 mod 3. It doesn't simplify as easily as that. All right. Move on. I'm going to skip these for now because they're very similar to what we did last time. So let's do these two base problems. Should be really quick. Actually, make this base 5 to save some time. Base 5. I want that in base 5. Okay, so these should take 4 minutes. right? So basically, what we want to do here is we want to turn 222 base 10 and base 5. Okay, so you basically think, what's the largest power of 5 that can fit in 222? Well, it's obviously not 5. We have 25, 125. It's always good to list out the power of the 5 here. Oh, it seems like 625 is too big. So the maximum is 125. Let's subtract that. Should get 97. So we have 97 left. We have 125 in there. How many 25s can fit in it now? Well, 3, right? 3 makes 75. Subtract 75 here. We get 22. How many 5s can fit in this? 4, right? 5 times 4 is 20. So we'll have 2 left, and that's the 2 in the final digit. That's it. Okay, pretty straightforward. Next one's a lot easier, actually. You guys need to convert this to base 10. We have 2 times 4 squared plus 2 times 4 plus 2 times 1. Or basically, this is 4 to the 0. This is 4 to the 1. That's basically how it works. So basically, we've got, well, we can factor out the 2. Let's make something easier. The inside is 21, so this is 42. Base 10. Any questions? Alrighty. Now we're going to cover some new stuff. We're going to do arithmetic with bases. I covered this as like the last challenge problem in your number theory worksheet last time, but it was a challenge problem, not really expected of you to understand how to do this yet. So basically, this is what we're going to do, arithmetic with bases. We're adding, subtracting, multiplying two numbers in the same base, but it's not base 10. Okay, and want to give the answer in base 6. So there are 2 ways to do this, actually. One way is the long way. One way is the easy way, actually. It's not really easy. It's longer, and it requires less brain work, all right? It's more about writing stuff down. So basically, you could convert each of these to base 10, add them in base 10, convert it back to base 6. That's very hard. It's not very hard, but you can make a lot of mistakes along the way. So we don't really want to do that. We're just going to do all our math in base 6. I'm going to show you how we do this here. We're going to add these 2 numbers. You have to remember we're in base 6. 4 plus 2. Now, I'm literally teaching you guys how to add here. So this is actually pretty hard. So 4 plus 2 is 6, right? Shocking. 4 plus 2 is 6. But we can't write 6 there because we got to give all our numbers, all our additions in base 6. 6 in base 6 is 1, 0, right? So we put the 0 down here and we carry the 1. Okay? Is everyone following me here? Give a thumbs up on your screen. Does it make sense? So basically add them and then we put it in base 6. So we got 1 and 0. We carry the 1 because we can't put both digits in one spot, right? Now we add again, 1 plus 5 plus 1, that's 7. 7 in base 6 is 1, 1. Put 1 here, we'll carry the other 1. 1 plus 3 plus 2, 6. We put the 0 down here and we carry the 1. Basically, the 1 just adds itself down. 1, 0, 1, 0, base 6. Okay. That one's relatively easy compared to base 5. Multiplying, actually. So let's multiply 42 times 34 in base 5. Okay. 2 times 4. We're just going to multiply as normal, but convert everything to base 5. 2 times 4 is 8. But 8 is 1, 3 in base 5. So we put the 3 down here. We carry the 1. Now we do 4 times 4, 16. But we have to add the 1 up top, 17. But with 17 in base 5, what's 17 in base 5? That's 3, 2. And we have 3 times 5 plus 2. So 32 goes here. So we multiplied these 2 pairs. Now we'll multiply these 2 pairs. Just standard multiplication, all right? I'm sure most of you should know how to do this now. So now let's do 3 times 2, which is 6. And 6 is 1, 1 base 5. So the 1 goes here, we carry the 1. Now we do 3 times 4. 3 times 4 is 12, and we add 1 to get to 13. 13 in base 5, what is that? 13 in base 5, that's 2, 3. Okay, now we add them. Remember to stay in base 5 though. 3 plus 0, 3. Put 3 here. 3 plus 3 is 6, but that's 1, 1 base 5. Carry the 1. 1 plus 2, 3. So the answer, 3, 1, 3, 3 base 5. Okay, any questions? All right, that's good. I got two problems for you. 5 minutes. So first one, 45 base 9 times 88 base 9. I'll do the multiplication in base 9. So what I usually like to do, it doesn't really matter. You can write the 45 above the 88, but for me, it's just somehow, I just like to write it like this. It doesn't matter which way you write it. I'm going to multiply these. 88 times 45. I'm actually get more space here. We first do 8 times 5. That's 40. I have a table running here. 40 base 10. Well, how many 9s can I fit in that? 4. I can also fit in 4 extra. That's 44 base 9. But the 4 down here, the 4, other 4, moves up. 8 times 5 plus 4, 44 now. 44 base 10. What's that base 9? That's 48 base 9. 8, 4, good. Now we do this one. So 4 times 8, what is that? 32. 32 is what in base 9? You can put 3 9s in there, which is 27. Then we have 5 left over, so that's 35 base 9. Put the 3 up here. 8 times 4, add 3, 35. 35 base 10. It's going to be 38 base 9. 38 here. Now we just need to add 4. 8 plus 5 is 13 base 10, which is 14 base 9. 1 plus 4 plus 8, what is that? Also 13. 13 is 14 base 9. 1 plus 3 is 4. 4, 4, 4, 4 base 9. Okay. I don't know how that happened though. I just wrote down 2 random numbers to multiply, and we got 4, 4, 4, 4. Not very good luck. But okay, let's go on to the next part. What is that number minus 1 in base 4? Let's see what happens. 1, 0, 0, 0, 0, 0, 0, minus 1. 0 minus 1 won't work. 0 minus 1 won't work. We got to borrow from the first one. Remember, this is 4. So when we borrow from the first one, that turns into a 3, and this turns into a 4. We borrow from this one, this turns into a 3, this turns into a 4. Borrow 3, 4, 3, 4, 3, 4, 3, 4. Now we can subtract. 4 minus 1 is 3. 3 minus 0, 3, 3, 3, 3, 3, 3. Oh, this one's supposed to go to 0. So we took 1 out of it, right? So 3, 3. I think that's too many 3s. Be careful here. So I think we rewrite that. Make sure I have enough 3s. There it is. So 6 3s, base 4. That's the cool thing, right? Whenever you have so many 3s, if you add 1 to it, it goes up to the next level because you've already filled up all your if you think about your base your blocks here, you have 3 small blocks, 3 strips, 3 flats. They're all full. If you add 1 more, it goes all the way up and it makes a new big block. Okay, a new place value. And that's the same thing that happens with 9, 9, 9, 9, 9, 9, 9, 9, 9, base 10, right? If you add 1 to it, it turns into 1, 0, 0, 0, 0, 0. Same idea. Okay. Now we're going to do digits. Digits are actually very easy. So a digit problem, these are 2 examples of the digit problems you're ever going to see. Find the blank digit in blank. So for example, it could be find the tens digit in 2 to the 50. Something like that, okay? Or it would say find the number of digits in 2 to the 50. All right, those are basically the 2 possible types of digit problems they're going to ask you. Find the blank digit, or you could say, oh, ones digit. Okay, it'll say find the ones digit in 2 to the 50, or find the number of digits in 2 to the 50. Okay, so one out of those 2. One out of those 2. And there's definitely going to be a visible pattern, so you don't actually have to solve for 2 to the 50 to find what the ones digit is. So for example, I have this problem here. What's the last digit, or basically the ones digit, of 7 to the 2343? right? We don't know what that is, but there's probably a pattern that's going to go on. So let's write 7 in the first. What's the last digit? 7. 7 squared, 9, which is because it's 49. If we multiply 9 by 7 again, because we really only care about the last digit, right? If we multiply 49 by 7, that'll give us 3, because we did 9 times 7 to get 63, right? But we don't care about whatever's in front. So all we need to do is multiply the last digit by 7 again. So we get 3, multiply 3 by 7, 1, multiply 1 by 7, we get 7. Oh, look, if we keep multiplying by 7, we'll do the same cycle again. So it cycles every 4 terms. All right. So this means if we go all the way to 2, 3, 4, 3, this basically cycles mod 4, right? Every 4 digits cycles over and over again, okay? This number is 0 mod 4. So basically, we just need to match. What is 2, 3, 4, 3 mod 4? And we match it to 1, 2, 3, or 0. 2, 3, 4, 3 is 3 mod 4. Use your divisibility rules, because you know that 2, 3, 4, 0 is 0 mod 4. If it's 3 mod 4, we target the 3. The last digit must be a 3, okay? Any questions here? So basically, any digits problem, there always has to be a pattern every single time. And you just have to find that pattern, okay? Every single time, okay? So whenever you see a digits problem, write out the numbers, write out the first few terms, and figure out what the pattern is, okay? 2 really quick ones here from Mathcounts competition. We'll do the first one. The second one is very, very similar. Basically the same thing. And let's do the first one here. Find the pattern. All right. So this one, look for the pattern. So first write out the units digit of the first few numbers. Okay, so units digit of 1 squared is 1. Units digit of 2 squared is 4. 3 squared is 9. 4 squared is 6. 5 squared is 5. 6 squared is 6. 7 squared is 9. 8 squared is 4. 9 squared is 1. 10 squared is 0. If we do 11 squared, we only care about the units digit, which is basically the same thing as just doing 1 squared. So if we do it from here on, it's going to be 149656941. Repeat. Because the units digit just repeats over and over again. So the squares of the unit of the units digit of the square of that integer is going to repeat over and over and over again. Okay, so we want to find what's the units digit if we add all these together, all the way to 2015. So that's basically saying, what is this whole number mod 10, right? What's the remainder when this is divided by 10? Well, 1 plus 9 is 10, and that's 0 mod 10, so those go away. 4 plus 6 is also 0 mod 10. Those all go away. As you can see, all we have left is 5, and that 5 is adding to this 5. Everything else is gone, which means that if we add these together, they also cancel. Okay, so basically, every group of 10, we have a 5 left, okay? Which means that all we need to do is find the number of groups of 10 all the way up to 2010. Is it even or odd, right? Because if we have an even number, then we have an even number of 5s here, which means that they all cancel each other out. If we have an odd number of multiples of 10 in this number, then we have 1 5 left because everything else canceled. 2010 is an odd multiple of 10, or it's at least it's 10 times an odd number, which means the remainder is 5 at 2010. If we go to 2015, all you have to do is add some more. 1 plus 4 plus 9 plus 6 plus 5. And here we are at 2015. 1 and 9 cancel, 4 and 6 cancel again. 5 and 5 also cancel. Units digit is 0. Okay, so basically when it says what's the units digit, think what is the remainder of mod 10, right? Because that's basically what it's asking. All right, I'm out of time now. So hope you guys enjoyed today, and I'll see you next week, Sunday. All right, bye. If you have any questions, you can stay behind and ask me anything you want.